Hello everyone, welcome to Numerical Methods class. In this video, we will talk about Chapter 1, which is about the mathematical modeling and engineering problem solving. And we will have a parachutist example as you can see on the right hand side. So let's first start with the engineering problem solving process. Simply, an engineering problem solving process starts with a problem definition as you can see on the left hand side. We basically identify the problem, state the objectives, and make a list of them. And based on these definition of the problem, we will need to generate alternative solutions or a mathematical model to be able to solve this problem. And in here we can use some problem solving tools, computers, statistics, numerical methods, graphics, etc. And this can come from theory as well as from data. And data part is the experimental part. And as you can see here, most engineering problem solving employs two prolonged approach. The first one is the empiricism or the experimental data, and the second one is the theoretical analysis. So simply these can go side by side together, and also we can use them separately depending on the problem definition. Once we have this mathematical model, then we need to solve it and have the results. The results can be numerical or graphical. And here the societal interfaces, scheduling, optimization, communication, public interaction, etc. can be used. And once we have this, we will need to evaluate the alternatives by using these results. And then finally, we need to implement the best alternative or the best solution, which gives the best results for us. And this kind of an engineering problem solving process is used for both problem solving as well as the design processes in the engineering area. Next, let's define what mathematical model is. A mathematical model is a formulation or equation which expresses the essential features of a physical system or process in mathematical terms. You can see here a representation of the mathematical model, and the f function here represents the mathematical model, and it actually results a dependent variable, as you can see on the left hand side, which is dependent on some variables or parameters which is shown inside the function. Independent variables, parameters, are forcing functions are two terms used in the functions or mathematical models. Here, if we want to define these, the dependent variable reflects the behavior of or the state of the system, basically the result of the mathematical model. The independent variables are dimensions such as time and space, along which the system's behavior is being determined, and these are independent from any other variables. So they are just entered to the system independently. The parameters, on the other hand, reflect the system's properties or composition. And these are separate from the independent variables, and they can be some constants. If we think about the term variable, these are variables which can change, but the parameters can be constants which doesn't change. Also the forcing functions, and these are the external influences acting upon the system, such as the force which applies to the system, for instance. So there are three characteristics of a mathematical model. First, it describes a natural process or system in mathematical terms, which is actually the definition of the mathematical model. And it represents an idealization or simplification of reality, because in reality there can be a more complicated physical phenomena, but with a mathematical model we can simplify it. For instance, we can ignore the friction force while defining some physical processes, and we can assume that the environment is frictionless. Third, it yields producible or reproducible results, and consequently can be used for predictive purposes, which means that we can use a mathematical model repeatedly to receive the same result, or by changing the parameters or independent variables or forcing functions, with different results we can obtain by using the same mathematical model. In this class, we will define a simple mathematical model, and then we will define a complex mathematical model to have two different examples for understanding the mathematical model. So here you can see a simple mathematical model, which is basically a Newton's second law, F equals m times a. And here F is the force acting on the body, m is the mass of the object, and a is the acceleration. Basically, by simply multiplying the acceleration by the mass, we can calculate the force. But here we need to convert it to a mathematical model representation scheme. As at the bottom, I put the representation of the mathematical model, and we need here an f function with independent variables, parameters, and forcing functions, which gives us a dependent variable. In this formulation, the dependent variable is the acceleration. Actually, when we apply a force, which is the forcing function, and m is the constant, that's why we can define it as a parameter. By dividing the force by the mass, we can simply have the acceleration, and that's why the acceleration actually is dependent on the force applied on the system and the mass of the system. So in this simple case, there is no independent variable because we are not yet predicting how acceleration varies in time or space. In other words, we assume that the a is constant, and that's why there is no time or space change. So that's why there is no variable of them, variation of them, and no variable, independent variable.